Welcome to demo session 3 of the course FPGA-based signal processing systems. In this demo, we will be demonstrating 4 examples, 2 of Moore and Mealy machine each, one example of a sequence detector that will also illustrate the dumpfile, dumpvar, dumpon, and dumpoff commands, how to store file and how to make a .vcd file and how to store the required variables in that. And the last one, example 4, would be a memory bank, how to store, how to create and store data in a memory bank. These 4 examples, the simulation of these 4 examples would be demonstrated in this session. And these examples have also been covered in the lectures taught in the course. So the first example is a Moore state machine. Basically, it is this machine with the state transition as shown here. As you can see, it doesn't require any inputs. Once a state is there, it just transitions to the next state as shown in the diagram. Based on this diagram, it just transitions to the next state at the next clock cycles. So how to describe this and how to describe this behavior through code? So here we have written a code for it, and this code is also covered in the lecture 22, that Moore state machine. So module name is SM1 demo 3. Input is clock. Output are sreg and xnext. So sreg and xnext are defined as registers. The parameters means based on how many states we have. Suppose here we have how many 1, 2, 3, 4, 5, 6, 7, 8 states are there. So 3 bits would be sufficient. So parameter the width is 3 bits, and all the parameters have been named as a up to h, means ABCD up to h, and they are equal to 0, 0, 0, 0, 0, 1 and up to 1, 1, 1. And then no input is required. The state machines, the code for state machines normally have 3 different parts. That is state memory, then a state memory where we define what the we evaluate what the snext is, and then next state logic, that is based on what logic snext would be evaluated, and then finally the output. Here in this state machine, we don't have any output, and we don't. So we will just be coding with a state memory and next state logic. That state memory always at the rate of positive edge of clock. sreg will be evaluated based on this snext, and it's a non-blocking statement. Then next state logic would be means based on what logic that evaluation is done. It is always at the rate of positive edge of clock, and sreg. This begin and block would be executed, means it would look for the sreg, which case is present at the moment, means A, B, C, D. If A is there as seen in the diagram, if A is there, it will go to next state would be E. If E is there, current state, then it will go to C. If C is there in the next clock cycle, in the next positive edge of clock, it will go to F. It is like this. So it is defined here. A, if present sreg is A, then snext is E as in the diagram. If B, then snext is A. If C, then snext is F, and likewise up to this H. If H, snext is D, and by default, we need to define a default case also here. Otherwise, otherwise it will create a latch. So this snext is equal to A by default. So it snext equal to A means it is this initial state, the firstmost state. By default, it will be here. Snext will be this. Then we will end the case statements, end case, end this begin block. So begin end is closed, and then we will close the module, end module, and module and end module. Now the test bench for this module name is SM1 demo 3 TB test bench. TB is test bench. Inputs clock, that is a reg. Outputs are sreg and snext. These are 3-bit outputs because in total 8 states were there, as we could see in the diagram clearly. Then instantiation, SM1 demo 3, this is the module name, SM1 demo 3. This is the module name, SM1 demo 3. So we are instantiating it. Then we will initialize the inputs we can note that we don't have any other input apart from the clock. Clock is the only input that is there. If the machine is in a particular state, at the next clock cycle, it will go to the next state as defined in this next state logic. That's all. We don't have any other input apart from the clock. Then this 100 nanosecond for global reset to finish this, we have provided 100 nanosecond global reset, 100 nanosecond delay. Then add a stimulus, we will be adding a stimulus. Stimulus is again just the clock, so we need to define the clock, that's all. So this always block is a sequential circuit, so clock would be in there anyway. So hashtag 50 means the time period would be 100 nanosecond clock, and this initial begin. Again, we need to monitor the different variables. So again, in an initial begin and block, we would use this display command and monitor command and list out the variables that are to be monitored, that are clock, then sreg, current state, and snext, that is the next state. Now we will run it. Here it is, clock. These are the clock cycles. Sreg is a current state, and snext, it is evaluated at the same instant as it is as it is shown here. It is evaluated the same. Here it is evaluated at the same instant. It will be assigned at the end of the clock cycle, at the start of the next clock cycle. So it is assigned at the start of the next clock cycle. Likewise, 0, 4, 2. 2 is evaluated here itself based on this sreg and assigned at the next clock cycle. So 2, this will be the current state. Then again evaluation of next state would be evaluated and assigned at the positive edge of clock, like this. So these are the different states. So this was example 1. It was Moore machine. Next example is a Mealy machine. That is we will be using a sequence detector code to illustrate that. It's an overlapping sequence detector 0101. Overlapping means I will show in the diagram. So this is the 0101 state transition diagram. This ABCD overlapping means if 0101 sequence occurs, it will give one output high, that is found, equal to 1. If another 01 occurs at this point, it will again show high based on this overlapping part. If it is 01 had already come in at the previous clock cycles, it will consider that also, again show high if the next 2 bits are 01. So it is that overlapping case. So it is the code for this, and it is covered in the lectures as well. We will just be demonstrating how to simulate it. That's all. So the module name is sequence detector 2. Input are clock, reset, and sequence. It's a Mealy machine. So this sequence input is also there, and then output is found. Output is again defined as 2-bit output, that is sreg, sreg, and xnext. Based on the number of states, means we have 4 different states as you can see in the diagram. So 2 bits would be required. So the parameters are all as well as the sreg and xnext are all 2 bits. Parameter names are A, B, C, D, and they are all 2 bits, 2-bit 00, 2-bit 01, up to 2-bit 11. Then, as I told in the last example as well, that state machine codes have 3 parts, that is state memory, next state logic, and output state logic. So here in state memory, that is always at the rate of positive edge of reset or positive edge of clock. If reset is high, that if reset is 1, sreg will go to this state, that is default state, this A. Then if sreg, else if clock is clock is high, that is the positive edge of clock. If clock is high, then sreg will be evaluated to xnext. As next state logic, s next is means next state, and the logic that it will follow is described here. That always at the rate of sreg or sequence. Sreg means current state and sequence is the input. Begin, this case statements would be searched for, means or looked for. So if it is A, if case, if sreg is A and if sequence, that input is 1 bit 1, s next would be A, else if it is not 1, means if it is 0, s next would be B, as shown in this diagram. At A, if a sequence is 1, at A, if sequence is 1, s next would be A, else s next would be B, that is if sequence is 0, it will go to B, and outputs are 0 in both the cases as shown in the diagram. So similarly, we will map everything here. B, if sequence is 1, 0, s next would be B, else C. Similarly for C, D for 0, else A. If sequence is 1 at D, then s next is C, else B. And by default, it is at A. A is the firstmost case, this A. Then we will end this case statement and the begin block, that is begin and is closed. Then again we will give the output state logic, because outputs are there as well. Outputs are there as well for every transition. For every transition there is an output. So we need to write them too. Always at the rate of sreg, that is the current state or sequence input. Begin, if sreg is D and sequence is 1 bit 1, found equal to 1. Means if it is at this state D and input is 1. Input is 1. It means we have already found this 0101 sequence, 0101 sequence. And so output will be 1, found equal to 1. Else, if it is something else, then found equal to 0. Then we will end the module. And this is the test bench. Inputs are reg, clock reset sequence. Outputs are wire, found and sreg, instantiation. This is a module name, this module name. Instantiation is done. Initial begin, initialization. Clock is equal to 0. Apart from the clock, we have reset signal and sequence also. See that they have been initialized. Then some delay is provided for global reset. Then stimulus are here. In this case, the stimulus that we have taken, just for understanding, we have given the stimulation stimulation in 2 initial begin blocks. So how will it executed? How will it be executed? Means initial begin block at t equal to 0, simulation time t equal to 0, clock reset and sequence are all are 0. And then at hashtag 100, means after 100 nanosecond of t equal to 0, it will wait up to that. And then again after hashtag 10, means 110 nanosecond, reset equal to 1, 120 nanosecond, reset equal to 0. And these stimulus 2 are in an initial begin block. So they too will be executed with reference to simulation time equal to 0. So display and monitor, these variables are listed out. They will display and these variables will be displayed and monitored. And this hashtag 10, sequence equal to 0, this input will be given not after this, but after 10 nanosecond from the simulation time 0. So basically it is like this: simulation time 0, sequence equal to 0, simulation time 10, sequence equal to 0, simulation time 20, sequence equal to 1. It will follow up to this. But yeah, simulation time 0, clock reset sequence equal to 0, simulation time 10, sequence equal to 0, simulation time 20, sequence equal to 1, simulation time 30, sequence equal to 0. And then these inputs would come at simulation time 120, 130. After these inputs have already been fed, these inputs would follow. They are in different initial begin blocks. So just for illustration, I gave you this. And then we will end this initial begin block, and then always, as it is a sequential circuit, now we have to define a clock as well. So this always and clock time period is 10 nanosecond, we will end the module. We'll run simulation. So you can see that these are the clocks. This is the sequence, and found means 0 1 0 1. It is found. Found is high 1. Then again, it's an overlapping case. So it's 0 1 0 1 again. So found again. So this is high 2 again. And these are the different states. Means 4 states are there in total. So 1 2 0 0 0 1 1 0 like this. So this was a Mealy machine. Means 0 1 0 1 overlapping sequence detector. Now we will come to the next example, which is again a sequence detector, but in the test bench we have put dumpfile, dumpvar, dumpon and dumpoff commands to illustrate how we store variables in a VCD file, not VCD file. So this is the file source code, and this is the test bench. Test bench is this. Module sequence detector, input clock reset sequence, output found, and output srange out that is of 2 bits, because in this sequence detector also we have 3 states, so at least 2 bits would be required. So 2 bits would be sufficient. 0 0 0 1 and 1 0, these 3 states are there, and it's a sequence detector. So always at the rate of positive edge of a reset or positive edge of clock, state memory is defined like this. If reset is 1, it will be in the default state 1 A. If clock is 1, if clock is high, then S next would be evaluated based on this next state logic. srange or sequence, that is always at the rate of srange or sequence. If A and if current srange is A, current state is A and sequence is 0, it will remain in A, else B, else it will go to B. If it is in B, then and sequence is 1, then S next would again be B, else it will go to C. If it is C and sequence is 1, it will go to B, else it will go to A. So by default, default case has to be defined, because else otherwise it will form a latch. So by default, S next is A, end case, end. In output logic, if srange is C and sequence is 0, then found equal to 1, else found equal to 0. And this is the test bench. Similarly, we would define the inputs: reg, clock reset sequence, outputs wire, found, and srange. Instantiation, then instantiation of the module sequence detector. Detect initial begin, that means these are the stimulus, global reset, and we have commented these stimulus out. Instead, we have provided a random sequence generator here. So it will generate a random sequence. So hashtag 10 C executed this random command is there. Initial begin will monitor the different variables using this clock, reset, srange, sequence, and found. They are all monitored. And here, after closing this block, we will again start this initial begin block. In that, we will provide dump file. Name the file that is to be created. This sequence dump.vcd. Dump variables, that is one sequence found. So sequence and found are the variables that are to be dumped. And dump off and dump on means the dump off after hashtag 600 means it will dump off after this much time. Means it will stop storing the variables in the file at this instant. And dump on means after stopping at this instant, and then after 100 nanoseconds, it will start storing the variables again up to the end of the simulation, up to the end of simulation time. end and end module. We will run this code. And we can see the log file as well, where it is 1. 100, it is 1. Similarly, 100, it is 1. Whenever sequence of 100 occurs, this row is for sequence. This is found. So wherever 100 is occurring, then output is 1. Similarly, in the this waveform editor window, you can see that this sequence. It is 1 0 0 1 0 0. So 1 occurred. 1 0 0. So 1 occurred. 1 0 0 1 occurred. It's like this. And this file needs to be searched sequence dump. Here, sequence dump.bcd. Sequence dump. So here we can see that two variables are there. Yes, these two variables are there. One is we can match it actually with the log file. Suppose it is this 43500. 43500 will go to that 43500. 1. So this is found at 44500. 44500. It is 0. So 4452, it is 0. So on, and these exclamation marks, whatever follows the exclamation marks, they are actually sequences, and these are found variables with this double quotes. So this is how with time it is stored, all the two variables. Now we will move on to the next example, which is a memory bank. This is the memory bank code, and this is the test bench for it. In memory bank, input are address, chip enable, and output is the data that is stored in the memory. Declare 4 separate memories. Means these are actually memory blocks. Means it has a width of a width of 4 bits. Means each memory is of 4 bits, and the depth of memory is again 4. That is 4 rows are there in. Suppose memory 0 is there, so 4 inputs would be there in it. 4 means 4 bits of 4 bits each. 4 rows would be there. So similarly for memory 1, 4 bits data would be of 4 bits each, and 4 rows would be there. Means 4 such data would be stored. So these are 4 cross 4 sized blocks. Now wire 1:0 TMP temp. This is used to generate addresses, like a concatenation of address 1 and address bit 0. Address is again a 4-bit input. So in this 4-bit input, 0 and 1 bits are concatenated to generate this temp variable, TMP variable, to identify which from where data is to be read. We will show this. So in initial begin, we will initialize all we will initialize the memory data like this. Memory 0 is this. Memory 0, address 0. So as I already told that memory 0 has 4 rows. That is depth is 4. So memory 0, address 0 has contains 5. This is the data. Memory 0, address 1 contains 12. This is the data. Memory 0, address 2 contains 0. Memory 0, address 3 contains data equal to 9. Similarly, for memory 1, 4 addresses are there as depth is 4. At 0, 14 is the data. At 1, 7 is the data. 2, 3 is the data. 3, 11 is the data. Similarly, for memory 2, 6, 1, 15, and 8. And for memory 3, 4, 10, 13, 2. These are the data, and it is initialized like this. Then assign TMP equal to concatenation of address bit 1, address bit 0. So it's a 2-bit a 2-bit variable TMP, and then we will assign data equal to this ternary operator. Ternary operator will check if chip enable is 1 bit 1 and address 3, that is address bit 3 is 0, address bit 2 is 0, that is it is 0 0, address is 0 0 and chip enable is 1. If it is found to be true, then memory 0, TMP is this, the lower bits 0 and 1. Whatever is contained in this row of memory 0 would be stored in data. That is, suppose it is address is 0 0, address is 0 0 means it will go to memory 0, this memory 0, and if it is 0, if found to be 0 again, it will store 5. And if it is not found to be true, it will store high impedance Z, that is high impedance state. Similarly, for data equal to chip enable equal to 1, address is 0 1, 3 is 0 and address 2 is 1, then it will go it means it is it has to take data from memory 1, and TMP based on this address, it will either take 14, 7, 3 or 11. Similarly, for if this condition is found to be true, it will go to memory 2, and based on this these lower 2 bits TMP, it will either select this 0 or 1, 15 or 18 and assign it to data. Similarly for this case, and we will close the module here. There is the test bench. Module name is memory bank test bench. Inputs are address and chip enable. Inputs are, you can see inputs are what? Address we are checking and chip enables. So, range CE, chip, inputs are defined as range, wire as wires, and the data is of 4 bits, so 0 to 3, integer I. I is used to generate addresses actually. So we have, that is an integer. Using this for loop, we have generated addresses. Then instantiation, memory bank. Memory bank was the name of the module. This is the name of the module, mem bank. Initial begin. Initialization means address is 0 at t equal to simulation time equal to 0. Chip enable is 0. Simulation at simulation time equal to 0. We'll close it. And we have to monitor the different variables. So again, in a begin in block, we will display address and data and time. And we have listed out in monitor command also time, address, data. Then for generating addresses, because address needs to be generated here for, I will show. For I equal to 0 and I is less than 16, because we have 4 cross 4 blocks, 4 cross 4 size memory. So for 4 is 16, 16 data is there. So 0, I equal to 0, I less than 16, I equal to I plus 1, address equal to I. So based on this for block, I will be generated. It will go from 0, 1, 2, 3 up to 16. And then we will generate a this hashtag 50 means at time period 50 chip enable will be generated, means it will toggle actually, means it will be 1 and then it will be chip enable will be low, then it will be 1, it will be low, it will be like that. Whenever chip enable is 1, it will follow this logic to check with using this ternary operator and assign data. Whenever chip enable is low, it will assign Z value, that we can say. And the addresses, these addresses are generated, means address for selecting memory, means memory 0, memory 1, memory 2, memory 3. For selecting those addresses, means the higher bits would be used. And once one of these memory is selected, the lower 2 bits, this that is used to generate TMP, and that will select one of these 4 values. So those addresses are generated here using this for loop. So now we will run this simulation, run behavioral simulation. So this is the editor window. as see, these are the from 0 to starting from 0 to f, or if you want to show in binary 0 0 0 0 0 0 0 1, so it is like this. It will go up to 16 different states. 0 0, the first two bits are this. The first two bits are this memory. Will select will select one of these four. Means either memory 0, memory 1, memory 2, or memory 3. And the last two bits, the lower two bits, would select one of these four data. Means either 0, or just 0, or 1, 2, 3, like this. Similar, and Z, you can see, means as we had defined like this, at chip enable equal to 1. Whenever chip enable was 1, this will be found to be true, and memory 0 TMP, this will be assigned. And whenever chip enable is 0, there Z will be assigned. Z is high impedance state. So chip enable is whenever chip enable is 0, Z is assigned. Else the data as found through the address, this lower two bits, and this for data mining memory, the data is split. So this ends the fourth example of memory band, and this ends part 1 simulation of demo 3. Here we covered one example of Moody state machine, one of Mealy state machine, one example of for demonstrating how we use dumpfile and dumpvar commands with dumpon and dumpoff, and the last illustration, this is for memory band. Thank you.